Welcome back to the fourth and final part of my talk. In this part, we're going to talk about the spin 7 case, the case of Cayley submanifolds. And lest you think that this is going to be a repeat of part 3 of the G2 case, it's going to be very surprising that the Cayley case turns out to be quite different from all the other cases. And we don't really understand why. We have some idea why. I'm going to talk about why it's so different a little bit, but really it's quite mysterious. So here's the setup. We have an 8-dimensional Riemannian manifold with a spin 7 structure. Remember, that's a special kind of non-degenerate 4 form. And it's a calibration. This is the calibration form. And just as we had for the G2 case, this 4 form, by raising an index with the metric, it determines what's called a vector cross product. So the cross product takes 3 tangent vectors and gives you a tangent vector, and it's defined by cross product of UVW inner product with Y is what you get when you plug all 4 of those into the 4 form. Okay? And we do not assume that the spin 7 structure is torsion free, that phi is closed. Okay, so the Cayley submanifolds can be defined. They're not necessarily minimal unless phi is closed. Here's the first major difference between the G2 case and the spin 7 case. The space of spin 7 structures is not open in the space of 4 forms. Right? In the G2 case, if you take a non-degenerate 3 form or a non-degenerate 4 form and you just wiggle it a little bit, it's still going to be non-degenerate. That's not true in the spin 7 case unless you move along a particular curved direction. There's a nonlinear embedding of the space of non-degenerate 4 forms. They're also called sometimes admissible 4 forms within the space of 4 forms. More specifically, if S is the space of spin 7 structures on a given 8 manifold, and you look at the tangent space to the space of spin 7 structures at a particular spin 7 structure, then this turns out to be the sum of these 3 spaces. These are the irreducible summands of the space of 4 forms with respect to the decomposition into spin 7 irreducible representations. The space of all 4 forms has 4 components in it. The self-dual break up into 3 pieces, and the anti-self dual is irreducible. And the tangent space to the space of spin 7 structures is these 3. So that means that if you move in the space of 4 forms, if you start at a spin 7 structure and you move in this direction, you are not going to be a spin 7 structure, okay? Even to first order. I'm not going to define what these spaces are. It's not important. For the experts, you know exactly what they are. But what I am going to say is that these two together give you symmetric 2 tensors. And this is really what determines the variation of the metric, right? This is the pure trace part, and this is the trace-free part. Sorry, what did I do? That's wrong. I apologize. It's this with this, is what I meant to say. So this is the pure trace, and this is the trace-free part for the metric variation. Okay, so that's the major difference. Okay, so now suppose we have one parameter family of spin 7 structures passing through phi at time 0, and its velocity at time 0 is going to be some 4 form, sigma, but because this is a path of spin 7 structures, its velocity at time 0 is going to live in this proper subspace of the space of all 4 forms. And so we can't demand that it's moving in the direction of exact 4 forms. The most we can demand is that it's moving so that its velocity at time 0 is the projection onto the tangent space of spin 7 structures at that point of something exact. Right? We can't assume that sigma is exact, but we want it to be the projection onto this subspace of something exact. Okay. And now let's take our family of special variations of the metric to be exactly those that are induced from paths phi, such that at time 0, the velocity of phi is the projection onto the tangent space of spin 7 structures of something exact. That's the obvious thing we can do, given that we have this sort of complication, right? This is the closest analog to what we've done in in the first two cases, the first three cases. And here, just an aside, as I told you in the G2 case, if you're curious, phi dot is sigma. It has a 1, 7, and 35 part because it's a tangent vector to the space of spin 7 structures. Then this phi dot will induce infinitesimal variation of metric, G dot, which is H. And the way you get H is, again, similar to the G2 case. You contract sigma with phi on two indices, on three pairs of indices, to get a 2 tensor, and you take some multiple of the symmetric part of that minus its trace. Okay, minus some multiple of its trace. But again, this is not trace free. And you'll see this will be important in a few minutes. Okay? So, with that out of the way, let's figure out what theorem A should be saying. So suppose L is calibrated with respect to phi. It's a Cayley submanifold. Okay? Then what we want is to say that for variations of metric in this special class, we want it to be true that the metric is critical for the volume functional, that the time derivative at t equals 0 of the volume of gt is 0. Unfortunately, it's not true. Right? We didn't expect this to happen. We were surprised when this happened. We thought we had made a mistake. We checked it a dozen times. It's not true. Why? Well, let's keep going. So what we need to do is to modify the class of directions in which we're varying the metric. This choice that we made on the previous slide isn't the right choice. Okay? So before we find out what the right choice is, let's go and look at theorem B. Okay? So this is exactly what worked in the co-associative case, where we had a 4-form that we were varying. So let's try the same thing in this case. So we take the same function that's been showing up in all the cases, the half the distance squared to the submanifold. We take its gradient, we plug that into the 4-form, and then we plug in 2 more vector fields to get a 1-form, and then wedge with those 2 vector fields to get a 3-form again, where V and L have the property that, V and W have the property that they're tangent to L and linearly independent on L. And then what happened in the co-associative case was that for exactly this type of variation of 3-form, we got that the time derivative of the volume functional at time 0 was 0. But in this case, if we take d phi dt, remember we had to project onto the tangent space of spin 7 structures. So if we take d of this and then project onto the tangent space of spin 7 structures and take that to be our velocity for the path of spin 7 structures, then this is not critical. So theorem B also fails for the obvious choice of particular variation. However, something really strange happens. If we throw away this one part, the one-dimensional piece, and only project to the 7 plus 35, then it does work. Right? So this is telling us that the right theorem B should be, okay, we take this as our test variation, but we throw away the one part. There's no reason we should throw away the one part except that it doesn't work if we don't throw it away. So we want to do pi 7 plus 35 of something exact. Okay. So this observation above here motivates us to first consider what the right theorem B should be, and from there figure out what the right theorem A should be. Okay? So as I said, it's going to be the following. Suppose that the volume functional, suppose that the initial metric g at time 0 is critical for this volume functional with respect to all variations of this form. We vary the 4-form, the Cayley form. We vary it in such a way that its derivative at time 0 is the projection of something exact but only onto the 7 plus 35. No pi 1 part. Okay? If that's true, if G is critical for such variations, then L has to be Cayley, has to be calibrated with respect to phi. So this is the sketch proof. Again, this is similar to the G2 case. If you take F as before and take eta to be as follows, then you compute with respect to an orthonormal frame after a lot of hard work. You get that the time derivative at time 0, again, is some non-zero constant, which I think is minus a quarter or minus a half, doesn't matter, times this, right? And again, the integrand is non-negative. It's a sum of squares of norms of vectors, and therefore this has to be 0. So therefore the cross product of v and w and ea has to be 0. For any tangent vectors v, w, and ea, the e's are a tangent frame. So it follows that the cross product of any three tangent vectors is tangent, and that's exactly the defining property of being a Cayley submanifold. Okay? So the proof of theorem B is very, very similar to the proof of theorem B for the associative and the co-associative case, except you have to throw away that pi 1 direction. Okay, and I'll come back to this in the last slide. So let's go back to theorem A for the spin 7 case, right? What we would want to be true now that we know what's the right class of variations of metric where we can make theorem B work, we would want theorem A obviously to be a converse of theorem B. So this is what our wish is for theorem A, our desire. If L is calibrated, if it's Cayley, and the family of metrics is such that its initial velocity, that it's induced by a family of spin 7 structures whose initial velocity at time 0 is the projection onto 7 plus 35 of something exact, then we would want G to be critical. Right? That would be exactly the converse of our new theorem B. But this is also false in general. This really surprised us again. We didn't expect that to happen. This is what actually happens. So here's a sketch proof of theorem A. This is a false theorem A. Let's see what goes wrong. Okay? So since our submanifold is assumed to be calibrated, it's a Cayley submanifold, we can find a local orthonormal frame for M which is adapted to the spin 7 structure. I'm not going to write down explicitly what that means, but it means that the vectors are related by the cross product in some way. And then you can compute the time derivative at time 0 of the volume of GT, and after a lot of miraculous cancellations again, then you get up to this factor, you get d eta minus star d eta. This is the star upstairs on the 8 manifold. Okay? The first term goes away by Stokes' theorem, but the second term does not. This is in general non-zero. We take this eta, which is this eta over here, we take d of it, that's a 4 form. We take the Hodge star upstairs, that's still a 4 form, and then we integrate that over the submanifold. And there's no reason for that to be 0. Okay? So, what do we do? Why did theorem B work then? If you go back and you look at the eta that worked for theorem B, this thing better integrate to 0. Right? And if you go back and you look at that form from theorem B, what happens is that you can actually calculate that star d eta, it doesn't just integrate to 0, it actually restricts to 0 on that submanifold. So definitely this does hold for that special variation that made theorem B true, that made theorem B work. Okay? So what have we concluded? We actually have a theorem A and a theorem B. They're converses of each other, exact converses. We have to do the following. The special class of metric variations that we're allowed to do are those metrics that are induced by varying the 4 form, the Cayley form, in the direction such that its time derivative at time 0 is the projection onto 7 plus 35 of something exact, so there's no pi 1 here, and we also need to assume that the integral over L of star d eta is 0. if we assume those properties for these metric variations, then theorem B and A and B are true. If L is calibrated, then G is critical for all such variations. And if G is critical for all such variations, then L is calibrated. Okay? So we did find our theorem A and theorem B. It looks very different from the associative and co-associative cases for two reasons, right? There's this problem, and there's this dropping the pi 1. So notice that this second condition here depends on the submanifold, right? The fact that we need star of d eta to integrate to 0 on L depends on the submanifold, and that's not good. We don't want our condition to depend on the submanifold. But this is similar to what happened if you go way back to part 2 of my talk. Theorem A, in the case of a UM structure, there were 3 cases of theorem A. Case 1 was when the real dimension was 2. That was very easy. And case 2 was when the real dimension was bigger than 2, case 2 and 3. And in that case, if the kth power of the Kähler form was varying in the direction of exact forms, everything was good. But if the first power of the Kähler form was varying in the direction of the exact forms, but not the kth power, then we had to assume something about the submanifold for the theorem to be true. But that condition we had to assume was always true if we assumed omega to be closed, if we assumed something about the torsion. So this is what I just said. In that case, in the case of higher dimensional almost complex submanifolds in a manifold with a UM structure, we got a condition for theorem A that depended on the submanifold, but if we assumed that omega was closed, we still didn't need to assume that J was integrable, but if we assumed that omega was closed, then that condition we needed to be true was always true. Okay, so the class of metric variations did become independent of L. So it's natural to assume that maybe if we assume that the calibration form is closed, that there's a torsion-free spin 7 structure, then maybe this class of variations of metric here, even though this second condition seems to depend on L, maybe that'll be true for any Cayley submanifold. Okay? But we've proved that in fact that's not the case, right? Just because you assume that the torsion is 0 for the spin 7 structure doesn't make that condition automatic for any Cayley submanifold. In fact, in general, it's not. It doesn't hold. Okay. So what have we got to summarize? There are 2 major differences in the spin 7 Cayley case versus the other cases we talked about. First of all, the space of spin 7 structures is not open in the space of 4 forms. Right? We already discussed that. It's almost the same thing in the UM structure case, because if you look at the space of non-degenerate 2 forms in that setting, that's the positive 1,1 forms. That's not open in the space of all 2 forms. But it is open in the space of 1,1 forms. It's a cone in the space of 1,1 forms, and we're not varying J in the UM case. J is fixed. It sort of decouples, right? We have a J and then we have an omega or a G equivalently. Okay, but J is fixed, and therefore we can just look at the fixed subset omega 1,1 of the 2 forms, and then the positive ones are an open subset there. And of course, in the G2 case, associative or co-associative, it really is an open condition on the space of 3 forms or 4 forms. But also quite mysterious, in the spin 7 case, we had to remove the omega 4,1 component of phi dot. Right? We needed to say that the path of spin 7 structures that's allowable is one whose velocity at time 0, of course it has to be a spin 7 structure, and we wanted it to be the projection of something exact, but it can't have a pi 1 component. And therefore, the G dot, the time derivative at time 0 of the family of metrics GT, ends up being something which is trace-free. G dot has no pure trace part, only a trace-free part. What that means is that we need to look at metric variations which are infinitesimally volume preserving. And of course, not just any old infinitesimally volume preserving metric variation. It has to come from the 4 form in this complicated way. But contrast that with the other cases, especially the associative and the co-associative cases, because not only did the trace part of the metric variation not cause any trouble in those cases, but it actually has to be there to make everything work out correctly. Remember, I said in the associative and the co-associative cases, there's this miraculous cancellation. If you try to say, let's move in the direction of the projection of an exact form where we remove the pi 1 part, then it fails. It doesn't work. Okay? So exactly the thing that you have to take away in the spin 7 case is exactly the thing that has to be there in the associative or the co-associative case for theorem A to be true. So we don't really understand why that's happening. It's quite mysterious. So it'll be very interesting to try to understand exactly why the spin 7 case is so different from the G2 case. That's all I wanted to say. So thank you very much for your attention, and I look forward to answering some of your questions when we do the question and answer part of the conference. Thank you.